Hello, thank you for being here. I'm Jodie. I'm from North Yorkshire. I'm a postgraduate ecology and biodiversity student at Newcastle University, and I'm going to talk about the research I conducted for my undergraduate earth science dissertation. So I looked at how climate-driven changes to the Greenland ice sheet's exports of melting ice may potentially impact primary production in the North Atlantic. So what exactly do I mean by all that? Well, as our climate is changing, researchers have generally observed gradual rises in air temperatures over Greenland and a darkening of the ice sheet's surface, amongst other things. And these effects are understood to at least partially explain the changes that have been seen in the Greenland ice sheet's mass. Over the last few decades, the ice sheet has been shifting from an overall balance in mass each year to annual net losses of many hundreds of gigatons of ice, meaning the melting in summer months is now outweighing the accumulation in winter months. And currently, it's generally predicted that these patterns are likely to continue and accelerate in the future. So one specific example of the changing face of the ice sheet is known as the dark zone. This is a strip of ice along Greenland's southwestern margin that is gradually expanding and growing darker due to algae growing more and more on the surface. And this darkening causes the ice to have a lower albedo, which means it reflects less sunlight and absorbs more of it. And this encourages melting to become more rapid and long-lasting. This is exacerbated by the Arctic summers simultaneously growing warmer and longer. So the climate-driven changes such as those I've mentioned are understood to cause the ice to melt. And if this melted ice, often called meltwater, doesn't refreeze or remain within the ice sheet, it will flow outwards through fords at marine terminating glaciers and through rivers routed to land terminating glaciers until reaching and being incorporated into the seas surrounding Greenland. It should be noted that surface melting isn't the only source of these exports, so others include ice calving, where often these great chunks of ice are broken off at the terminals of glaciers, and also submarine melting, where convecting warm sea waters cause melting at the subsurface. And not only that, but meltwater isn't the only type of export. There are also icebergs being exported outwards into the surrounding seas, and in fact, icebergs make up around half of all of Greenland's exports, with meltwater making up the remaining half. And these icebergs being exported from Greenland are somewhat mysterious in that their compositions and transportation patterns haven't been very thoroughly studied, especially when compared to that of other ice sheets such as the Antarctic ice sheet, and it's partly because of how difficult it is to study them and also the lack of interest in them until recently. The distinctive features of icebergs are also often overlooked in modelling studies that are trying to understand Greenland's melting and exports, and this is partly due to our limited understanding of them. Icebergs have complex compositions which are challenging to measure objectively with our current study methods. For instance, the few existing studies of the nutrients in Greenland's icebergs vary greatly in their outcomes, and measurement methods often involve a subjective visual judgment with the naked eye of the proportion of sediment that they contain. Unlike in the case of meltwater, the nutrients in icebergs are trapped and are unavailable for organisms in the water to take up and use, and much of the exported ice reaches offshore in solid form. This implies that icebergs are capable of transporting a greater proportion of these nutrients to offshore ecosystems than meltwater, and so they may be worth taking into consideration when modelling these systems, and I'll come back to this shortly. But anyway, why might these exports to offshore ecosystems be important? Well, one reason is because they may affect the primary producers residing in these waters. And you might think, well, what are those? In this context, I'm referring to phytoplankton, which are these tiny microscopic algae that live in the upper layer of the seas known as the euphotic zone. And the primary production refers to their activity, as they are photosynthesizers and they are responsible for producing around half of our planet's oxygen. And they're also the foundation of most marine food webs, so they're vital to life on Earth in multiple ways. Their activities and ability to thrive are of course dependent on their nutrition, and the incoming discharge from Greenland could potentially influence this in a multitude of ways. And by discharge, I'm referring to the meltwater and iceberg exports. Phytoplankton primarily depend on sunlight, and the main source of nutrition for them around Greenland tends to be deeper seawater that is rich in nutrients and is upwelled to the surface. But we know that certain nutrients exert control over their productivity, particularly to the west of Greenland, and we've also seen that when researchers insert additional nutrients into these areas, the primary production increases. So this suggests that primary production isn't at its limit and could increase if their nutrient supply is increased. This isn't an isolated thing though, and there are other factors to consider as well. So at the same time as this, meltwater coming from Greenland can induce what's called stratification in these offshore waters, which essentially means the upper and lower layers of the sea become more separated, which reduces the amount of nutrients coming from that deeper seawater. This has led current models of this whole system to generally predict that as Greenland's melting and discharge increases, primary production in these offshore seas will reduce because of this stratification. However, these models assume that the meltwater and icebergs themselves don't contain any nutrients. This is due to factors such as organisms taking up much of the nutrients in the meltwater before they reach the sea, and some of these models don't include icebergs at all. Now, relating back to what I said about icebergs, knowing what we know about how icebergs trap nutrients, carry them across a greater distance, and make up about half of all of Greenland's exports, it may be that the significance of nutrients in icebergs has been overlooked in these models so far, and so this is what I chose to investigate. So I put together a highly idealized model to simulate the whole process. So that involved, of course, the Greenland ice sheet itself, the nutrient contents of the ice and meltwater, and the transportation patterns to see where these exports go and how they get there and so on. I was unfortunately unable to conduct an in-the-field study myself, so the selection of study locations was guided by the availability of existing data. Spatial coverage of the Greenland ice sheet and its surrounding seas is quite patchy in existing research, and so I developed the model based on a select few study locations, and then my results would ideally then be upscaled and generalized to represent larger areas. So here is a depiction of the study areas. I chose the northern region of the Labrador Sea as my offshore study area, which is shown here on the left in pink. And almost all of Greenland's discharge entering this region comes from southeast and southwest Greenland, and so these were my study areas of the ice sheet, shown in orange and yellow here. This worked out quite well because the southern sectors of Greenland are the ones that produce the largest amounts of discharge, and so they attract the most interest in the study area and so have the most data available for them compared to other parts of Greenland. As for the nutrient contents of the exports, only a small proportion of the ice sheet has been assessed directly in this way, mostly at ice cores and the most accessible outlet glaciers around the edges. The widest range of data was available for 3 of these outlet glaciers within southern Greenland, shown in green, purple and red. The exact bounds of their catchments are seen here to the right, with catchments just meaning the areas of the ice sheet where the water collecting into the outlets is coming from, and the general catchment areas are shown on the map on the left as well. So you can see that together their catchments cover a fairly good amount of southern Greenland. I also took into consideration the underlying bedrock geology of Greenland. So although the grip ice core shown on the map here doesn't fall into the bounds of southern Greenland, it does share the most dominant underlying rock types with the southern sector, especially the southeastern sector. So that's the Paleoproterozoic shown here in purple. So it was also included as an additional source of nutrient concentration data as well. My 3 study locations were also underlain by rock types that make up the large majority of southern Greenland too, so this also worked out quite well. So next I needed to think about which nutrients to study because not all nutrients are essential to phytoplankton, and they can also only use the nutrients when they occur in certain forms, which are called bioavailable forms. These factors guided my selections of which ones to study, and these turned out to be nitrogen, phosphorus, silica, and iron. All of these occur in various dissolved and particulate forms, and I selected to study those of which that are generally understood to be at least mostly bioavailable to phytoplankton. Nitrogen and phosphorus are commonly understood to be the primary limiting nutrients of phytoplankton, meaning they are nutrients that exert the most control over them out of them all, but they additionally require silica and iron. For example, a type of phytoplankton called diatoms have an outer cell wall that's made almost entirely of silica, and phytoplankton also require iron to undertake a variety of processes, such as utilizing nitrogen and conducting photosynthesis. So I put together the model, set up my assumptions and that kind of thing. I ran the model, I got some results back, and my findings varied a lot in terms of how much the different aspects fell in line with existing predictions in published literature. For example, my predicted fluxes of particulate iron from meltwater and icebergs overall were quite like that of other studies, whereas my predicted fluxes of dissolved iron in icebergs specifically was a whole order of magnitude higher than existing estimates. As well as this, my calculated fluxes of nitrogen were 1 to 2 orders of magnitude greater than that of phosphorus, which is to the contrary of predictions in previous studies involving both icebergs and meltwater. But it's important to consider the fact that the majority of nutrients in meltwater are lost before being exported offshore, as organisms within Greenland, such as algae, and in its coasts too, will take them and use them, whereas, as I mentioned earlier, this doesn't apply to icebergs. And to understand this in a more meaningful way in this context, we've got to look at the relative contributions of icebergs and meltwater to these nutrient fluxes. So it turned out that icebergs dominated the fluxes of all 4 nutrients I studied, as can be seen here. And this was especially true in the case of iron, with over 99% of all iron in Greenland's exports coming from icebergs. Overall, icebergs were responsible for exporting 97% of the total bioavailable nutrients. This does suggest that when we take into account the ability of icebergs to lock in their nutrient content and transport it over longer distances, that their nutrients exported from Greenland may not be as negligible as is commonly assumed. But to understand how these nutrient exports relate to phytoplankton, we need to consider their specific nutritional needs. So their nutritional needs are usually described in terms of something called stoichiometric ratios, if that's how you pronounce it, which is just a ratio of how much of each nutrient they require. Often this just includes nitrogen and phosphorus for phytoplankton, as they're the most thoroughly understood, but extended ratios including silica and iron have been developed, and so I used the extended kind. And so here is that ratio. So from left to right, we have nitrogen, phosphorus, silica, and then iron. And the sizes of these bubbles here just roughly represent the relative amounts needed of each of them. So this is the ratio of the nutrient requirements. And here is my calculation of the nutritional content of Greenland's meltwater exports and of the iceberg exports, and this is after removal processes that have taken place on their way out of the ice sheet. So this shows that both exports have more silica and iron than the phytoplankton need relative to nitrogen and phosphorus. So it can be said that they're oversaturated in silica and iron, especially in the case of iron in icebergs, which is almost 500 times higher, so you could say it's supersaturated in iron. Since the vast majority of nutrients reaching the study area get there via the icebergs rather than the meltwater, the iceberg ratio dominates the overall ratio. And so here is the nutritional ratio of Greenland's exports overall. and it deviates a lot from the stoichiometric ratio of phytoplankton in that it's oversaturated with silica and supersaturated in iron. But could these nutrient fluxes be enough to increase primary production in the northern Labrador Sea? Well, as for the levels of nitrogen and phosphorus, even though they're higher than previous estimates, they're still relatively low when compared to that of the rich seawater that enters the euphotic zone where phytoplankton reside, especially since the bulk of these fluxes I calculated occurred in particulate forms, which are likely to be less bioavailable than dissolved forms. Furthermore, if runoff is undersaturated in nitrogen, this can enhance stratification, separation of the layers of the water, and thus impede the supply of nutrients from upwelled seawater, which could even result in dilution of the euphotic zone and leave phytoplankton with lower concentrations of nutrients than they had before. Most of the discharge received by the northern Labrador Sea originates from the southeastern sector, and this sector is dominated by marine terminating glaciers. Now, dilution is less likely with marine terminating glaciers than with the land terminating counterparts, so this issue of dilution may be less of a concern in the case of the northern Labrador Sea than the wider North Atlantic. The results are quite different for the oversaturated nutrients though. While not a lot stands out about the silica fluxes, the dissolved iron flux in icebergs is an order of magnitude higher than previous estimates, and when you take into account the specific characteristics of icebergs, these fluxes of iron may be more significant than often assumed in relevant modelling studies. Researchers have experimented with adding dissolved iron alone into North Atlantic waters, with the result being an increase in primary production. And so if these fluxes coincide with already adequate levels of nitrogen and phosphorus in the northern Labrador Sea, it may be that these fluxes of silica and iron, or really just iron, could potentially enhance primary production in the area. So upon looking further into this, with the amounts of silica and iron being exported, the potential enhancement is pretty minor in the case of silica, but noteworthy when it comes to iron. If we consider the nutritional content of the exports in isolation of their other effects, we might expect a slight increase in total primary production in the northern Labrador Sea from the silica, and more than a doubling of the total primary production as a result of the iron. Now, of course, in reality, this effect of the meltwater and icebergs won't take place without the other effects also taking place. So once we consider the nutrient limiting factors of stratification, for example, any enhancement as a result of silica is just unfeasible, but a modest iron-induced enhancement may well be plausible. So in order to develop this model, to represent the system of everything going on and study it, assumptions had to be made, and these assumptions tend to simplify the more complicated reality of what's actually taking place in real life. So for example, when it comes to the aspect of time, so the timings of when phytoplankton in the northern Labrador Sea are active and could be influenced by the exports versus when the exports actually arrive. The periods of greatest melting, known as the ablation seasons, typically run from June through to August in southern Greenland. More specifically with my study locations, this season has been found to reach its peak at Leverett Glacier in July, and at Sermelik Ford the season runs into September and peaks in July and August. Phytoplankton in the northern Labrador Sea typically have 2 annual blooms, meaning 2 periods in which their numbers grow the most. So there's the spring bloom in April and the summer bloom beginning in July, peaking in late July to August time and running until August or September. This summer bloom is thought to constitute about half of the area's total primary production annually. It's been found that the summer blooms temporally correlate with the arrival of southern Greenland's exports, where the bloom develops about a week after it arrives and lasts until the inputs drastically reduce, and it's been theorized that this might be related to incoming iron. In the major melting event that took place in 2012, exports from southwestern Greenland were observed reaching the Labrador Sea within mere days, which was followed by one of the sea's largest blooms on record. But on the other hand, the southeastern exports have to travel between hundreds and even thousands of kilometres via the east and west Greenland currents before they will reach the northern Labrador Sea, and this process can take months. So it seems unfeasible for these exports to reach the study area in time to have any effect on spring blooms or the initiation of summer blooms. However, they may reach the site in time to lengthen the summer bloom and support the primary production in that way. Now, when it comes to the nutrients that are transported, the model oversimplified the way they will behave in multiple ways. So, for example, it's generally thought that about 90% of nutrients in meltwater are removed on their way out of Greenland before they're exported offshore. So this was one of the assumptions I made. And another assumption made was that icebergs retain all of their nutrient content. However, in reality, of course, the icebergs are going to melt to some extent and make some of the nutrients available to be taken by other organisms before they reach the study site. And this is also the case for both the icebergs and the meltwater on their way to the study site. This would likely affect the southeastern exports more than the southwestern ones, as they take much longer to get there. But due to the lack of existing studies on the exact nature of this, the extent of this effect is quite unclear. Adding to complication is the fact that not all forms of nutrients studied are completely readily bioavailable to be used right away. For example, dissolved organic nitrogen is thought to be up to about 70% bioavailable in a marine environment, and amorphous particulate silica isn't as readily available as dissolved silica is. If that wasn't confusing enough, nutrients don't necessarily stay in their original state and may convert into more or less bioavailable forms with time, and the exact nature of these processes is pretty unclear, especially when working on such a large scale. For instance, the exact nature of how iron behaves in marine environments isn't very thoroughly understood, which makes interpreting how these fluxes may influence phytoplankton a lot more difficult. And to fully interpret how the influx of nutrients might affect the surface water concentrations in the northern Labrador Sea, the existing concentrations would need to be known, but in the case of iron, there haven't been any direct measurements taken as of now. Another spanner in the works is that it's not as simple as, well, as melting increases, exports into the study area will increase too in a nice, simple, linear fashion. And this is partly because the offshore exportation is facilitated by the ocean currents and the particular types of coastal wind patterns going on. These are known as upwelling favourable winds, and these act southeastwards in Western Greenland and direct more of the discharge offshore, basically. However, in summer, when melting is at its highest, winds tend to be more downwelling favourable, which constrains the discharge closer to the coast and acts against the offshore transportation. At the same time, though, increased amounts of meltwater have been found to potentially indirectly lead to a stronger forcing of the offshore transport, essentially by reducing mixed layer depths around the coast and enclosing the wind's power within a thinner layer. So, taking all of this into consideration, it's not very clear to what extent offshore exports will increase with the increased melting of the Greenland ice sheet. There's also the question of how reliably these findings at the study locations can be generalised to wider regions. While the majority of Greenland's exports entering the northern Labrador Sea are coming from the southern sectors, about a quarter are from other areas. For example, about 16% is thought to come from northwest Greenland. So a further look into this in the future might well give more of a comprehensive insight into the matter. Additionally, the northern region of the Labrador Sea is distinctive from the rest in multiple ways, with one way being that its phytoplankton blooms tend to begin and end later than those further south do, and it's unclear from these findings alone whether the exports would reach the rest of the Labrador Sea or the surrounding waters in time to support their blooms too. At the same time, observation of Greenland's rivers have found that the transportation speeds of meltwater and icebergs have been greatly increasing, as well as the velocities of outflow and terminal retreats of several major outlet glaciers. So This may mean that the exports could arrive downstream more quickly in the future if these patterns continue as they're expected to, which could in turn mean that they may have a greater influence on offshore blooms in the future. So, in summary, it appears that southern Greenland's exports of meltwater and icebergs may deliver larger amounts of bioavailable iron offshore than previously thought. And these iron fluxes occur almost entirely in the form of icebergs, so it may be that the importance of icebergs is underestimated in the relevant models. However, direct measurements of the Northern Labrador Sea's surface nutrient concentrations are really needed and are essential to understanding to what extent these iron fluxes may enhance primary production there. And finally, a further look into a wider range of Greenland's outlets, icebergs, and the relevant ocean transportation patterns will really help us to understand how much these findings represent Greenland and the North Atlantic at large. So that's everything. Thank you very much for your attention. I finished just in the nick of time before the sun fully goes down. A big thanks to the Natural History Society of Northumbria for this opportunity, and also to Dr. John Telling for his supervision of my research. Please feel free to reach out to me by email if you have any questions.